In this video, I would like to go over these memory model directives like constant, stack, data, and code, and open this handout right here for memory model directives. And these directives let us organize executable code and data variables and stack memory for temporary storage of data like local variables or functions in C. So logical segments contain three components of a program: code, data, and stack. So you can think logically that when we try to organize our program, we have this constant memory segment, we have this data memory segment in the program, and we also have the code. So the code here is pretty much including everything else right here in this area. So we have we're trying to basically, once we start placing things inside these areas of our assembler file, the things will be stored in these memory segments. So for example, as soon as we begin specifying things inside the code segment, so these procedures that we specify are going to be pretty much placed directly in this code memory segment. Once assembler processes this input file, we know that we can look at the listing file for precise definition of everything that assembler generates for us. And so each procedure here will just be sequences of executable instructions, and that's going to be the content of the code segment, as an example. So is the data and constant data right here. Everything is organized into these memory segment. In general, we have three logical segments, and they occupy this physical memory at runtime. There are three segment registers that contain information about the physical memory segments in real mode. But in protected mode, which is this memory model, the flat memory model, this is a protected memory model that's used by most modern operating systems, which allow multitasking and memory protection features. The segment registers become memory segment selectors and generally not available to a program running in protected memory mode. So these directives here, which start with the dot, we call them simplified segment directives, and they hide a lot of details of segment definition and calculation specific to operating system on which we're using our assembly programs. So every program written in assembler has basically one main module where the program execution begins, and it's designated by its special name, main. Any additional modules should contain only code and data segments. Okay, so the main module can contain both code, data, and stack segment definitions, like we have here, but the rest may only have the data and the code. So this is segment registers and the idea of memory segments that are controlled by these segment registers. So this is an example of something that we already been using many times as a starting point to populate our data and constant memory segment and the code with the stuff that we tried already. So this is a general idea, and stack size can be specified as well. So this directive opens and closes the stack segment with segment name stack, and it's just using the segment size, and the default segment size is 1 kilobyte. But since our programs that we've written so far really don't make a lot of different calls, we kept it to a minimum, and the smallest size of the stack is 100 hexadecimal, which is 256 bytes, or the smallest stack size that we can have. The end statement closes the last segment, which would be closing in our code the code segment, and the last segment is marked at the end of the source code. So optionally, we can also provide the program entry point, and this is where we specify and main, and this and main statement here in our assembly code specifies that the main symbol is pretty much the beginning of our executable code, and so that the linker will know that this is really where our program should begin to execute. So the first directive that is specific to memory model is the model directive, and defines the attributes that affect the entire module. So we can specify what is the memory model. The flat memory model essentially places all of these segments, the constant data segment, the data, and the code segment, into one large segment. Okay, and basically all of these segments, essentially const and stack and data, they all coexist in one memory space. Okay, so basically the access to everything, to the code, access to the data, access to the stack, is everything lives in one single segment. So basically addresses are consistent and unique in this entire segment. This is what the flat memory model does. So we also can specify naming conventions, which will be covered when we start talking about procedure calls and returns. And so additional parameters can also be specified. And in our case, the flat memory model uses the so-called simplified segments. That's what we just discussed right here. So the model must appear in source file before any other simplified segment directive. So this is why the model is very much at the top before any of these other directives that we use here. And really the important thing about the model is that when writing assembler modules to be used in combination with high-level programming languages such as C and C++, you should use the same memory model as the calling language. And that's for us, since this is the case, almost exclusively you want to use this flat memory model because it's used by C and C++ when compiler processes C and C++ programs. So these are additional ideas and definitions of other available memory models, and we're pretty much going to be focusing on the flat memory model in our coverage of assembly programming language. And there is this requirement that before we specify our memory model, we also need to provide the CPU architecture level. So that can be 386, 486, or 586, and so forth. So 386 is like the minimalistic version of the instruction set that we're trying to use in this assembly program. So it's basically like the target hardware platform that we're trying to specify. And of course the 386 is the lowest level that supports the flat memory model. So it's okay to stay minimalistic. So the operating system automatically initializes segment registers at load time. The operating system loader component automatically initializes, essentially configures all segment selector registers to properly point to all of these memory segments in our physical memory when the program executes. Also, what's really convenient with flat memory model here is that all pointers, and pointers of course are addresses in memory and memory locations, variables that specify addresses of objects in memory, addresses of code, location like procedures. They're all 32-bit and they're pretty much near, or type of them is near 32. So it's just like the in every memory model that you can specify with the model directive, there could be variations in between, ranging between the 16-bit, 32-bit, a combination of 16-bit with these registers in real mode. So this is good to know that besides the fact that all of our pointers are 32-bit, all of the procedure calls and initializers in different segments, they're all near 32 type, which is simple to use. So the flat memory model does not require the so-called far addresses, and far addresses have to be using 32-bit addresses combined together with these segment selector registers. So we don't have to worry about it. In general, these segment selector registers are not even available in flat memory model. So any kind of far addressing issues simply don't apply in flat memory model.